Recall what we have learned about the exponential and logarithmic forms of equations. If we know that three quantities, a, b, and c, are related in the following way, that c equals a to the b power, then we can also express this relationship in an equivalent form by saying log base a of c equals b. When working with these kinds of equations, we can consider a as a constant value. When we fix a like this, c and b are related to one another in a functional way. The first form can be thought of as an exponential function where b is the input, or independent, quantity, and c is the output, or dependent, quantity. The second form can be thought of as a logarithmic function where c is the input quantity and b is the output quantity. We have done a lot of work in class together to make meaning of these two forms of equations. Here, we give a word of caution. Remember that the equations must be in one of these exact forms before we can switch to the other form. And also remember that a, b, and c can be expressions rather than just one particular number. Sometimes we must use algebra first to transform the equations into the correct form before converting to the other form of the equation. For example, one of these two equations is in a form that is ready to be converted into logarithmic form. Which one is it? The top or the bottom? After some thought, we see that the top equation is in the proper form, but we must divide both sides of the bottom equation by 40 before it is in the form c equals a to the b power. For that bottom equation, c is 250 divided by 40, and a is 5, and b is x. Once both equations are in the proper form, we see that 3.5 equals 1.25 to the x power is equivalent to log base 1.25 of 3.5 equals x. And we also see that 250 equals 40 times 5 raised to the x power is equivalent to log base 5 of 250 divided by 40 equals x. Switching between these forms allowed us to find an expression for the value of x in these equations. In other words, we have solved the equations for x. But the problem is, it is sometimes hard to imagine what the values of these logarithmic expressions are. It would be helpful for us to have a decimal representation for them so that we can think with them. Some calculators allow you to enter logarithmic expressions with different bases, and it will give you a decimal representation of the number that you're looking for. But not all calculators will do this. This particular one does, and when we enter log base 1.25 of 3.5, this calculator will give an answer of 5.61416 when rounded to 5 decimal places. This means that if we take 1.25 and raise it to the 5.61416 power, it should equal a number very, very close to 3.5. Check on your calculator and see if it does. But how can we find this number if we have a more common calculator? We can use our knowledge of the properties of functions and the properties of logarithms. First, note that we know 3.5 is equal to 1.25 raised to the x power. So this means that if we put 3.5 into any function and 1.25 raised to the x power into that same function, then the output of the function in both cases must be the same number, because a function can only send one input to one and only one output in order for it to be a function. Because 3.5 and 1.25 to the x power are equal to one another, then their outputs must be equal when we put each of them into a function. So, let's put 3.5 and 1.25 raised to the x power into the log base 10 function, since all scientific calculators have this log function. This means that log of 3.5, the output of the log function when we put in 3.5, must equal the log of 1.25 to the x power. That's the output of the log function when we put in 1.25 to the x power as the input. Now we can use property 3 of logarithms to change the form of the right side of this equation into something that we can work with algebraically. Because of property 3, the right side of the equation can be written as x times the log of 1.25. Now we can use algebra to solve for x and find that x equals log of 3.5 divided by log of 1.25. So we can enter that information into our calculator, and we will find that x is approximately equal to 5.61416, just like the other calculator provided. One interesting and important thing to notice that we have done here is that we just changed the base of one logarithmic expression that we were given, which was 1.25, into another base, here base 10. Going through this process allowed us to find the value of the expression using our calculator, and this idea did a lot of work for us and will continue to do a lot of work for us. Use these ideas to think with as you solve all parts of questions 1, 2, and 3 in Module 4 Investigation 9 in the student workbook. Question 3 is challenging, and you will need to remember the relationship between percent change and growth factors to set up your equations. Remember, in problems like this, if we are given the percent change, say 15%, then the growth factor will be 0.15 plus 1, or 1.15. Also, if we are given the growth factor, say in this problem 0.92, then we can subtract 1 to find the percent change. Here, it would be negative 8%. Also, part B in question 3 adds an additional wrinkle. Let's see how well you can do with this challenging problem. So, submit your answers to questions 1, 2, and 3 in Module 4 Investigation 9 in the student workbook using your instructor's preferred method by the time and date that your instructor has identified.